Imagine a star that has already died, but it still spins like crazy and shoots out powerful beams of energy. It's so small you could cover it with a big city, but it has more mass than our Sun. This is a neutron star, the dead core of a big star, so extreme that it feels more like a monster than a normal star. And when that dead star sends out regular flashes that we can see from Earth, we call it a pulsar. Today, we're going to explore these zombie stars, how they're born, what they're made of, why some flash like a lighthouse, and how they help us study the weirdest physics in the universe. Everything starts with a very massive star, at least 8 times heavier than our Sun. Inside, it burns fuel in layers like an onion. First hydrogen, then helium, then heavier stuff, until it builds up an iron core. Iron is bad news for the star, because fusing iron doesn't give it any energy back. Without that extra push from fusion, gravity wins. The core suddenly collapses inward, and the outer layers fall in, then bounce out in a huge blast called a core collapse supernova. For a short time, that one dying star can shine brighter than billions of normal stars in its galaxy. If the leftover core isn't too heavy, it doesn't become a black hole. It becomes a neutron star instead. So what exactly is a neutron star? Well, it's one of the strangest things in the universe. It has around 1 to 2 times the mass of the Sun, squeezed into a ball only about 20 kilometers wide. That's smaller than many cities on Earth. Because all that mass is packed into such a tiny space, it is incredibly dense. A single teaspoon of neutron star material could weigh as much as a big mountain. The gravity at the surface is so strong that if you drop something from just a meter above, it would hit with more energy than a nuclear bomb. Inside, normal atoms cannot survive. The pressure is so huge that electrons and protons are crushed together to make neutrons. The star is like a giant city-sized atomic nucleus, made mostly of neutrons. When the big star collapses, it shrinks a lot. Just like an ice skater spins faster when they pull in their arms, the collapsing star spins faster and faster as it gets smaller. Some newborn neutron stars spin many times per second. Their magnetic fields also get squeezed and amplified. A neutron star's magnetic field can be 1 trillion times stronger than Earth's. A special type called a magnetar can have a field even 1,000 times stronger than that, the most powerful magnets known in nature. This insane spin plus the insane magnetic field is exactly what sets the stage for pulsars. Alright, let's talk about pulsars. Imagine a cosmic lighthouse, and you've basically got the idea. A pulsar is a special kind of neutron star, one that we see as a repeating flash of light. Now it's not actually blinking on and off. The trick is all in the spin. Think of it like this. A neutron star has a spin axis, the line it spins around. But it also has a magnetic axis, which is where it shoots out powerful beams of radiation, like 2 giant laser beams. The cool part is, these 2 axes are tilted. They don't line up. So as the star spins, these beams of light sweep through space, just like the rotating light from a lighthouse. If one of those beams happens to sweep past Earth, we see a quick burst of energy, maybe radio waves or X-rays. Then, as it spins around again, we see another burst. From our perspective, it looks like the star is going flash, 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 with an incredibly steady rhythm. Some pulsars flash a few times a second. But the really wild ones, called millisecond pulsars, can spin and flash hundreds of times every single second. Their timing is so precise, they're actually more accurate than some atomic clocks here on Earth. This amazing discovery was made back in the late 1960s by a young researcher named Jocelyn Bell Burnell. While studying radio signals from space, she found this incredibly strange pattern. Sharp, perfectly regular pulses, like a drumbeat coming from the cosmos once every second. At first, the team even joked that it might be a signal from aliens, labeling it LGM for little green men, but they quickly figured out it was a natural object. The only thing that could explain such a fast regular signal was a rapidly spinning neutron star. This was the first concrete proof that neutron stars, which had only been a theory until then, were real. Since that day, we found thousands of these cosmic clocks scattered all across our galaxy. So why do some pulsars spin so much faster than others? This is where we get into the recycled pulsars, the zombies of the star world. Many of these super fast millisecond pulsars live in a binary system, with a normal star. Over millions of years, the intense gravity of the neutron star pulls gas away from its companion. This gas doesn't just fall straight down. It forms a swirling, hot disk around the neutron star. As the gas spirals inward, it gives the neutron star a push, spinning it faster and faster like pushing a merry-go-round. This process recycles the old, slowed-down neutron star, spinning it back up to incredible speeds. It's a dead star, brought back to a new, hyperactive life by feeding on its neighbor. Pretty cool, right? But what if we crank up the crazy even more? Among neutron stars, magnetars are the real beasts. A magnetar is a type of neutron star, but with a magnetic field 1,000 times stronger than a normal one, and up to a quadrillion times stronger than Earth's. That field is so ridiculously intense that it can literally twist and crack the star's solid crust. When that crust breaks, it triggers a starquake, releasing a colossal burst of energy. These outbursts shoot powerful flashes of X-rays and gamma rays across space, sometimes strong enough to affect Earth's upper atmosphere, even from tens of thousands of light years away. Magnetars are rare, but they are a perfect example of what happens when magnetism completely takes over. They are another kind of zombie star, constantly stressed and shaking under their own insane magnetic fields. Now, neutron stars and pulsars aren't just cool space monsters, they're incredibly useful for science. Because pulsars spin with such precision, astronomers use them as natural cosmic clocks. By measuring tiny changes in the arrival times of their pulses, we can discover new planets orbiting them, or see how they slowly lose energy and spin down over time. Scientists are also watching a whole network of pulsars spread across the sky to hunt for very long, slow gravitational waves, ripples that stretch and squeeze space itself. On top of that, neutron stars allow us to study matter at unbelievable densities, several times higher than inside an atomic nucleus. By comparing observations with theory, physicists can test which models of extreme matter are right. Magnetars, in turn, help us understand super strong magnetic fields and how they can literally break solid matter. In short, these zombie stars are cosmic laboratories for gravity, nuclear physics, and magnetism all rolled into one. So neutron stars and pulsars show us what happens when nature pushes physics to its absolute limits. They are the tiny, ultra-dense hearts left behind when massive stars explode. Some spin calmly, some flash like lighthouses, and some rage with magnetic fits. But they all tell the same story. Stars live, they die, and they leave behind these strange remains that continue to shape the universe. Every time a radio telescope picks up the steady ticking of a pulsar, it's listening to the heartbeat of a dead star that blew itself apart long ago. The next time you look up at the night sky, just remember, out there in the dark, zombie stars are spinning, flashing, and keeping time for the entire galaxy. If you enjoyed this deep dive into the universe's lighthouses, don't forget to hit that like button and subscribe for more space stories. Thanks for watching.